The question that started our course was, what are real numbers? And in this video, we're finally going to give the best answer we can for that. In other words, we lay a logical foundation that tells you the most basic properties of the real numbers. In fact, what we describe are axioms for the real number system. If we want to prove something about the real numbers, then every step in our proofs has to be justified ultimately by these axioms, which might mean directly using the axioms or possibly using other theorems which in turn are based upon these axioms, or possibly theorems based on other theorems based on, and so on, down to the axioms. So we'll start with the axioms for a field. And you've seen these before, early in the course. These axioms are for all of field theory. Now, they don't go as far as we need to describe exactly what the real numbers are, but it's a start. They don't answer every question about the real numbers, which means we need to add additional axioms to this list. So in addition to being a field, the real number system is an ordered field. And we also said what that means in the earlier videos. The real numbers are naturally ordered by the less than relation. So we wrote down axioms for ordered fields, and again, that's still not going far enough. Next, we come to the axiom of completeness. And this is, in a sense, the big one, the one that really tells us what ordered field we're talking about, the completeness axiom. Now, I'm going to say that completeness, by definition, is really the property that Cauchy sequences converge. But I'll say a bit more about that in a moment. And then, in addition to that, you need a little bit more that the rational numbers are dense. And we gave an explanation of that property also in an earlier video. One way to say that the rational numbers are dense in the reals is to say that real numbers can be approximated very closely by rational numbers. For example, every real number is a limit of a sequence of rationals. Alternatively, between any two real numbers, there is a rational number. This set of axioms, taken together, will tell us exactly what we mean by the real number system. In other words, the real number system is the one and only number system satisfying these properties: ordered field, which is complete, and in which the rationals are dense. So, unlike our previous axioms for field theory, which described a large class of fields, these properties tell us exactly one and only one field, the real numbers. What we mean by that is that anything that satisfies these properties is isomorphic to the real number system. So then it means, you might be renaming things, but essentially the same properties. There's really only one thing that has these properties up to renaming. And it's the same notion of isomorphism that we have in any mathematical context. So we allow for some variation in notation. The aliens will have some other way of talking about the real numbers, presumably, and different symbols, but these are the basic properties. Now, there are other choices of axioms that can be used in place of these ones that I've listed. And here's a slight variation. For example, we can say just as well that the real number system is the unique ordered field which has the least upper bound property and in which the rational numbers are dense. So in the context of ordered fields, there are several equivalent ways to characterize the property of completeness. And in the top of the slide, we have the Cauchy property, which is that Cauchy sequences converge. Cauchy's criterion gives us completeness. In the context of the other axioms, the least upper bound property will be equivalent. And this alternative, the least upper bound property, is also referred to as the Dedekind completeness axiom. This Dedekind completeness axiom is not something that applies to general metric spaces because it requires ordering. But in the context of the other axioms, the least upper bound property carries the same power as the fact that Cauchy sequences converge. So these are two alternatives for a set of axioms for the real number system. Now, these axioms convey a lot of the other properties that I haven't mentioned along with them, including some properties that are sometimes listed as explicit axioms. For example, the real number system is an extension of the field of rational numbers. But you see, that's implicit in what we've written. There are many fields, and they're not all extensions of the rational numbers. But every ordered field does contain the rational numbers. Another thing that I haven't written down here is the Archimedean property. But that's also included in what we've written. It's implied by it, although some people will list it as an axiom. Now, from a logical point of view, these are very hefty properties. They're hefty axioms. Let's compare with the axioms of field theory. I'm just going to show you again the axioms of a field. And the thing I want to point out is that all the field axioms here, they have quantified statements, universal quantifiers, say for all A, B, C, D, that kind of thing, such and such hold. Now, all the quantifiers in the axioms for field theory quantify over the elements of the field itself. In logic, we say that field theory is a first-order theory because we have universal and existential quantifiers over the elements of the field. Similarly, the theory of ordered fields is a first-order theory. By contrast, the axioms given here for the real numbers require quantification not just over elements of the field itself, but over entire sequences of elements of the field. And this distinction might not stand out to you, but to a logician, this is a very significant step up in the amount of firepower here. It's not possible to write down axioms of the so-called first-order theory of reals, which uniquely characterize the real numbers. You can't do it with first-order properties. You need something like what we've given as a completeness axiom. Any version of the completeness axiom is a second-order statement, which means that it requires quantification over more than just individual elements. This fact is significant from the perspective of trying to characterize the real numbers in a way that does not allow anything else to satisfy these properties. There's another point where the nature of the axioms becomes relevant. Unfortunately, we use the word complete in more than one way in mathematics. In a logical sense, one says that the first-order theory of the reals is complete. But here we're not talking about the topological completeness that we've talked about up to this point. When we say that there's a kind of logical completeness of the real number system, at least the first-order theory, what we mean is if you write down a statement about real numbers using various algebraic operations, order relation, etc., all the notation that comes with the real number system. It's okay to use quantifiers as long as you quantify over the real numbers, but not over functions or subsets or sequences. Then such a statement in the real numbers is either true or false. If the statement is true, then there is a proof. If the statement is false, then you can prove that statement. And all of this can be done algorithmically. That there's a procedure for testing whether a statement is true or false in the first-order theory of the reals. The theory, in other words, is decidable. There's a procedure to decide if a given statement is true or false. And you might think that this is something that we take for granted, but no. And I have to say that in the natural numbers, we do not have any such completeness. We don't have decidability. And this is because of Gödel's incompleteness theorem, and the completeness part that is referred to in Gödel's incompleteness theorem is in this other logical context. The point is, in the natural numbers, or in the integers, there are statements in the first order theory that are neither provable nor disprovable. Moreover, there is no algorithm that's guaranteed to tell if a given statement is true or false. This was a shock to learn in the mathematical community, but it's just something we have had to come to accept, or embrace, I would say. Only in the 20th century this became known. So it might sound paradoxical that the natural numbers have a theory that is undecidable, that you cannot test in general whether statements are true or false. There are things that you cannot prove, cannot disprove. Well, in the first order theory of the reals, you can. There are reasons for this that I don't have time to elaborate on here and would not probably be appropriate in a real analysis class. But I should point out that the theory of the real numbers that we do here is not limited to first order theory. So we have a lot of statements that quantify over sequences, over functions and subsets. And that's largely what we care about with real numbers, is the second order theory. The completeness property itself is an example of such a second order statement. For the second order theory of the reals, there are certainly undecidable statements. Now, let's not wade into the deep waters that I was referring to there, but for our approach to providing foundations of the real number system, what I said was that I was just going to give you axioms. Here are the basic properties. And I would say, assume them and work with them. There they are. They're the axioms. Now, if you were hoping that I was going to actually prove those properties, then I would have to disappoint you, but I would say you can prove the properties that I listed as axioms, but then they would have to be in terms of things about the rationals, and it would require a lot of work, again, more time than I would be willing to spend in this particular course on real analysis. But I want you to be aware that it is possible to prove all the foundational properties, starting with a full understanding of the rationals. And then you would probably be saying, well, okay, but I don't want to assume things about the rationals. I want you to prove them. And I would say, okay, well, we can go back and prove them from properties of the integers. And then you could push that back even further to the natural numbers and ultimately base things in set theory with the Zermelo-Fraenkel axioms plus axiom of choice. But the point is, you have to start somewhere. You have to have a foundation somewhere. All of mathematics is grounded ultimately in some choice of axioms. Our choice to start with axioms of real numbers is a pragmatic choice made because we're talking about real analysis here. Nevertheless, it's good to know, at least in a nutshell, how the construction of the reals from the rationals works. Now, we've already seen one way to construct reals from the rationals. That's using equivalence classes of Cauchy sequences. That was a process described in the previous video. If you were to follow that approach, you could prove all the foundational properties of the real numbers that way by defining properties including completeness. They're provable through our construction using properties of the rationals. I also said that there was an easier way to get from the rationals to the reals, and I think you should also know about that approach. This is the method of Dedekind Cuts. Now, a Dedekind cut in the rationals is a partition of the rationals into two parts, I'll call L and R, such that every element of L is less than every element of R. Here's an example of a Dedekind cut. We partition the rationals into these two subsets, L and R, where you can see every element of L is less than every element of R. L and R stand for the left and right set of the partition. And this is another example of a Dedekind cut, just a slight variant of the first example. Some books will define Dedekind cuts in a slightly different way, but don't worry too much. But here is also a Dedekind cut. It's of a very different type. We again have a left set and a right set. It partitions all the rationals. Every rational is either in this left set or in the right set. You can define this partition using just the theory of the rationals. I've written down how you would do that. But knowing what you do know about the reals, you say, oh, I see what you're doing. You're just splitting the real line at root 2. Everything to the left of root 2 goes in the left set. Everything to the right of root 2 goes in the right set. And yes, that is the partition you get. But I want to define it in a way that only calls upon properties and an understanding of the rationals. Because the point of this is to use the rationals to construct the reals. If you don't know what square root of 2 is, how are you going to define this partition? And this is a way to do it without using a number that hasn't been invented yet. So by using Dedekind cuts, you arrive at a representation of the real numbers. So this third example of a Dedekind cut gets you to the idea of square root of 2, rooted in just the rational numbers, together with some constructions that come from set theory. So everything is going to ultimately use set theory, almost everything that you want to do in mathematics. But then set theory together with the rationals gives you a way to reproduce the real numbers. And you can use Dedekind cuts to verify all the defining properties of the reals, including the ordered field axioms, the completeness, and the density of the rationals in the reals. This approach is faster than the approach using equivalence classes of Cauchy sequences. And this construction of the reals is very important for historical reasons. Now, the main reason why I emphasize the other approach is that Dedekind cuts are pretty much good for one thing, whereas Cauchy sequences are an important tool not only in real analysis, but throughout mathematics, including settings where there's no order relation. It's a more general approach.